Yeah. It works. Okay, so let me start first by asking you, yeah, well, you know what, I should have used my clicker. You know, it's just completely dead, no? Interesting. No, it's very interesting. You see, well, that's what technology, it's certain things are very complicated. Okay, trying again. Okay. Yes, fantastic, fantastic. Yeah, the more simple technology is supposed to be, the more harder it is to figure it out, right? Anybody here is familiar with eBPF? Okay, you know, some hands, that's wonderful. Because I was so much afraid you guys will be all familiar with eBPF and much better experts than myself, right? And that will make me miserable. Now, hopefully, I have some stuff to share with you which will be useful. And in this presentation, we'll talk a little bit about the eBPF overview, and as well, I'll share with you some examples how I see eBPF being helpful in practice, what for, and how. First, let me start with how eBPF is different, right? Different compared to what? Compared to their conventional, or you can also talk about it as a static Linux kernel instrumentation, right? If you think about how the Linux kernel is instrumented and was implemented before eBPF, there was this bunch of counters and timer which is sprinkled around the kernel space, which would include various counters, which then get exposed again through various vehicles. The most well-known one is procfs, right? And then you can use various front ends, such as vmstat, top, iostat, right, which would read those counters, format them, do some math, and expose that to you, right? So what is the problem with this approach? Well, obviously, amount of instrumentation you can get this way is limited by the overhead, right? If you have way too many of those counters and timers, the kernel will be slowing down. And then also, who decides what is implemented and how? Which particular kernel sections are going to be timed or counted, right? That will be by kernel developers making that choice, which may not match your needs as troubleshooting some particular problems. What I think is also interesting, and especially in this conference, right? If you hear about a bunch of talks from today and yesterday, we talk a lot about data being the most useful when it has contents, right? When you have sort of different pretty detailed buckets, when you have response time distribution. And generally, Linux kernel implementations has none of that. Well, maybe you have a counter of, let's say, I/O operations per different, block device, right? But we do not have more in-depth information than that. While it's very possible what you care, from I/O, for example, for different files. Right? Me, for example, being the database guys, for us, there are some things which are very special, like database transaction log file, because if the I/O gets stalled right into that file, then everything kind of freezes, right? So we want we would like to monitor that file in more details, but we cannot really do that on a kernel, Linux kernel level easily, right? And what that means, of course, is what you can go only so far going in the complicated issue in terms of information you have. In terms of eBPF, gives us dynamic information. You have probes which are dynamic. You can really put them in a very large amount of kernel places, and then you can have a flexible processing of that emitted data. You can consume it an event, you can build a histogram, you can place all kind of different buckets, and so on and so forth. And that gives you ability to instrument almost everything you want, and then you can really go into a very deep diagnosing particular cases. So that is eBPF value on a very high level as I see that. Now let's talk more about the eBPF and particular that's history in an implementation in Linux. I think what is fascinating is what eBPF originally doesn't even come from the instrumentation for performance sake, right? BPF is something which dates back to 1992, and that was efficient virtual machine for packet filtering, right, inside of a firewall, right? And for that what was extended, right, as a general event processing framework, and in that extended version included in the Linux version. That is what eBPF stands for. Now, because BPF itself is so old, many people starting to drop the E as well, right? So when you speak about BPF in Linux, right, or have a tool names, for example, BPF trace, that is the same as eBPF. You know, it just the E was dropped in a process. What is also great about this tool is or this framework is the newer versions. They actually have a JIT compiler with that, so it can be really high efficiency processing that instrumentation code you can put in. eBPF in Linux has been in Linux kernel since 2014, right? So for about 5 years right now, right? And because if you look at the distributions which people run in the kernels we have, we only start to see that really being very widely useful in production, right? Like if you look at the latest, right, or recent Red Hat, Enterprise Linux, Ubuntu, Amazon Linux, right? They already have a kernel which has actually quite good eBPF support. At the same time, eBPF is continuing to be improved very actively in the Linux kernel, right? So each version really has something which is better. Here is example of some things which are being improved in relatively recent kernels. And if you look about the improvements, it tends to be focused around kind of two different areas. One of them is things which we can instrument, right? What kind of data we can really get into the system. And the other is how we can store and process that, right, before that being emitted to the user process. So if you look at the eBPF programs, right, or how eBPF works, right, we get the trace point to which we can attach with a little probe, right, a little program written in that eBPF bytecode. These programs are actually verified when they are loaded in the Linux kernel to avoid this misuse. And that is wonderful. That is what this makes this technology more safe than compared to some older solutions which would require you loading some kernel model to enable instrumentation, because that is kind of scary to do in production. Now, I wouldn't say there is nothing you can do to break your kernel with eBPF, right? So for example, if you find some event which is triggered 10 million times a second, and if you put some very expensive probe on it, well, your system may be become so sluggish it is as good as dead, right? But it is much more safe than other approach. Now we get the CLang, their compiler, which can generate the eBPF bytecode. Something else which is interesting and important about eBPF is what the compilation is kernel dependent. And I think that is one of the problems we still see with eBPF, because often to run those tools you need the kernel headers installed. If you have some mismatch between the kernel version and the kernel headers, things don't work as expected, right? So it's a little bit more fragile, right, compared to the tools like vmstat, which is kind of always there, always work, right? You can rely on it. Now, eBPF is the bytecode, and it's kind of all the complicated. But I think a good thing is that right now we have a great tool set around eBPF, and few of us will need to write the programs directly. This is, if you ever wonder how eBPF bytecode looks like. Actually, the most simple way to get an example is using TCP dump, because guess what? TCP dump is also using eBPF, right, for getting the data it needs from a Linux kernel. If you look at the eBPF environment in Linux, here is the distribution between the kernel space and the user space. As many other graphs, I took that from Brandon Gregg's blog. He has a fantastic blog with a lot of material, a lot of talks on eBPF. If you really want to go deep, please make sure to visit that. And in this case, you can see what on those very far I spoke about is implemented on the kernel level, right? So it's not like somebody verifies the code and then loads that into the kernel, right? And you can easily, bypass that. But the safety thing, right, is a kernel driven. And then that shows you the different types of data eBPF can consume. If you look at eBPF in Linux, here is an example of the different tools and a subsystem, which is focused on the BCC, right? The BCC, that is a set of tools, collection for dtrace, and you can see there is large amount of tools exist which are focused on a lot of different parts of a kernel, which allow you to get that information without writing eBPF code. Here is another graph which shows the trace points which exist, right? What kind of those different things you can instrument in the different kernel version, right? As you can see, there is a lot of very cool stuff out there. If you look at the tracing landscape in terms of BPF, this is again coming from Brandon Gregg, and you can see there is a lot of tools in that ecosystem, and some of them are relatively complicated and hard to use tool, right? For example, raw BPF is extremely powerful, but writing that stuff is not for those who faint heart. And now we have starting to get a lot of more tools which are much more practical, like BPF or BPF trace or PLI, which are both quite mature and quite powerful. So I already mentioned about the BPF and the challenge of availability of that in Linux. I would say that has been improving a lot over very recent time. I remember then I would look into their, even like a year ago, doing this content, you would have a lot of distributions, so would not have a content, right? You would have to go to separate places, download packages, right? Or maybe recompile stuff yourself. Now we can see a lot of the distributions start to ship something in eBPF. But that adds another danger. You may have the packages for those actively develop utilities like BCC, for example, which are kind of outdated, and they don't have all the tools, right? Or the tools are not as good quality as you can get. So my recommendation, if you're using eBPF actively in your environment, right, try to get the fresh packages. There those packages lie in this IOVisor project. Right, so if you check that iovisor.org, right, of a repository on a GitHub for everything you need around BPF, right? They have tools, packages, and so on and so forth. Okay, now let's look at some tools and tools in action. One thing which we use a lot, right, is what we call the poor man's profiler, right? Say you have a, let's say, process which spends a lot of its time somewhere, maybe that's, CPU time, maybe not, or right, maybe it's waiting on some disk IO on a mutex, right, where that wait happens. You can actually do that with eBPF, right? So what we are doing here is we are looking at the all user plus kernel trace, right? And we can see what on the top side we have a certain thread, right, which is a MySQL thread, which is stuck in that iBooth merge and background function, right? If you know how MySQL works, right, that is actually quite helpful to understand what may be causing the load on the system. Now, anybody knows why are we using relatively strange number of sampling and 49 Hertz? Any idea why it's 49, kind of strange number? Not 50, not 100. Well, what's that? Well, that's right, right? So the idea is a lot of people by default say, hey, we'll do it at the rate of 100 Hertz a second, right, or 50 or 10. What that happens is a lot of programs still use kind of start of a second timers for doing their stuff, right? And if you always trace the threads at exactly the same point, right, at the same offset of a second, you may see the thing, right, which will not be representative of reality. Another great tool which comes with eBPF is BAL latency, right? That's traces a block IO and allows us to see the latency for the disk IO, right? Which I think is fantastic, and especially I found that helpful troubleshooting some complicated storage. Network storage in the cloud, something like EBS, because it may kind of in average perform well, but then you can find sometimes the sum of IO kind of stall for, very bad time, right? And having that information gathered and presented maybe to, the cloud folks to say, hey, deal with that is very, very valuable. What we can also see even a first case is the block IO given system or specific process is having, right? I think that also can be quite valuable to understand what the workload is really happening. Again, in terms of our the database workload, we often make certain assumptions about how large IO, for example, really gets submitted to the kernel, right? Or is your workload IO sequential or not? You can really understand that with that tool. What it also can be helpful if you're looking at the cloud, if you're using either like provision IOPS or you pay for IOPS. In many cases, you may be charged for IOPS independently on their size, right? So you want to make sure your IOs are more bulky, right? So you don't really pay extra. This is what comes on a block device. I think even more interesting is being able to look at this information at the file system level, right? Here I'm showing that for ext4 file system, then you can look at the timing for reads, writes, and for things like fsync. Again, if you look at the database world, the fsync, like really kind of physically persistent data on a storage, is a very important operation from a performance point of view. And depending on the storage and whatever environment, that is something which can be very expensive and can have some severe outliers. If you're looking at the outliers, so for outliers, you can also trace that, right? If you want to say, hey, you know what, is there any kind of IO starvation or something, performs, slower than expected? So in this case, I am looking at the tracing operations more than 10 milliseconds. Of course, I can configure that, right, to wherever, and I can see what operations by what process to what space to what files took more time than I expected. Again, can be very helpful in this case to understand why performance is not what you expect. The next one, which I find very helpful, is the cache stat information. One thing which Linux is missing, right, and probably because that's expensive, is really having a very good hit rate statistics for its cache. Right, you often know how much is the cache, but hey, you know what is exactly the hit rate to, right? To that. The eBPF trace, you can actually see that very well to see how many hits or misses your cache is having, as well as how many dirties, right? And that means how many writes to the cache has happened, right? Which you can then compare to the number of physical writes going to the storage, right? And see how much cache allowed to buffer stuff. What I find that's helpful is if you have a cache-intensive workload, right, to do some capacity planning, right, to run a test of different cache sizes, right, or different amount of data on the system, right, to understand how that impact performance and understand if some of that is related because cache efficiency drops down specifically. Another piece which is very great in this tool set is instrumenting the CPU. In a lot of cases, I see when people think about, oh, is the CPU problem? Look at CPU utilization. Oh, CPU utilization is 80% or 100%, right? That means it is a problem. But reality is, if I have, let's say, one CPU core, right, for example, and I run the program with just, doing total compute, right, I will have 100% CPU usage. That is actually not a problem at this point, right? Because if I add more CPUs, my program wouldn't run faster with just one thread. At the same time, if I would run, for example, 100 threads program, right, on the same one core CPU, I will also have the same 100% CPU usage, but with much larger oversubscription, right? What is a good way to look at that is really looking from the CPU run queue latency, which tells, hey, how long before the process became available to be placed on CPU versus when it was actually placed on CPU. And especially if you're looking at your interactive applications, you want to make sure that time is short, right? So there is no CPU scheduling delays, which happen typically due to CPU oversubscription. Now, another stuff which is not performance related, but I found that's very helpful for some, general kind of sysadmin troubleshooting, right? We get with a lot of kind of scripts which run other scripts those days, right? And often something goes wrong, and then you just say, well, there was an error somewhere. You don't really know where it comes from. With that exec snoop, we can actually understand what programs are being launched by different components in the system, and that can often help you to troubleshoot the problem, right? In this case, when developers did not get the decent error reporting built in the system. Here is another example which I use for the same post, tracing the open files. In many cases, I would get something like I run a program, it complains me saying, oh, blah, blah, blah is invalid. I'm saying, where the hell does that come from, right? Tracing what files that program actually reads and saying, oh, that used that weird config file, which I'm not sure where it comes from, can be very helpful to troubleshoot that. Another cool tool is eBPF, which you can use both from security standpoint and understand what's going on, is tracing TCP connections, right, which are being established. In this case, I would say that is not the only tool, right? You can also get that directly from Linux network stack, but I think it's a wonderful example to show how powerful eBPF is in terms of what it's usable for, all kind of use cases, not just performance analysis. What I use more frequently that for is looking at the TCP retransmits, right? Again, when you look at the database, in many cases we have the situation is what clients complain that the query was running slow, but when you look at the database, it was running fast, right? And the engineers say, well, you know what, that is something wrong with your database, because it's always the database is at fault, all the databases are nasty, ugly, and we hate them, right? Well, what we can do here is that we can actually trace the TCP retransmits, because obviously when TCP retransmits happen, then the delay is introduced in connection, and because we do not just get the number of retransmits, which is easy to get with something like netstat, but we know what connection that come from. We can see what client that was impacted, right? If you look at that and we can say, hey, look at that, that query instance was slow because exactly that. Another bits and pieces which is not very, I think, well instrumented in a lot of systems is this, lookups, right? Because if you think about you going somewhere and getting the request, right, on certain URLs, in many cases what you will have very well measured is how much that operation to fetch that content actually took, right? While DNS lookup actually may be the problem in terms of performance. I think that is especially important for reverse DNS lookups, because I have seen so many stacks where your kind of normal DNS lookups is very well monitored, very well architected, and so on and so forth. But the reverse DNS lookup can take a lot of time, right? Because it's not managed very well. If you look at it, all tools available in BCC, right? This is the list I took relatively recently. You can see there's a lot of stuff out there, to play with. Okay. So we spoke about BCC, and BCC is this great tool collections, which is very easy to use, right? And you can extend it by adding your own tools, but that is actually pretty hard. Now, I know many BPF, eBPF users have been looking for something as a dtrace backend. Then we do have that backend, which allows you to write relatively powerful one-liners, right? So you can really use that. And that is something which BPF trace allows, right? That is a very powerful backend which you can use for one-liners, right? So, for example, this one is a very simple one-liner but useful, right? That allows you to see all the system calls on the low level, which is available and you can connect, right? So it's out there. Or if you want to trace number of syscalls per process, right here is their number. So you can trace, right? And again, it's very powerful. As I mentioned, if you're really interested in eBPF, I would suggest to check with this page on the Brandon Gregg's website. It's amazing. The last meaningful thing I wanted to mention is eBPF overhead, which I think is important. As I mentioned, eBPF is fast, but you need to be still mindful and think about how often given trace point is triggered to compute the overhead. In this case, this was done by Cloudflare, right? Some benchmarks, and you can see what simple probes can take maybe about 100 nanoseconds, right, to execute more complicated 300 nanoseconds, which is actually pretty good, right? That means if you look at 100 nanosecond, that means 10 million of probe execution a second per core, right? But that still gives you an idea how much overhead you can allow. And the last slide, this is a nice link list, right? If you guys want to get deeper, right? Check out download the slides after conference, and you can read more about eBPF. With that, thank you. And I think. Okay.
We're a little over time, but if anybody has a burning question, they can't wait for Slack.
Burning questions. Yes, I think Jason made a hint. Get out of here, Peter.
Hey, I just carried all these cookies downstairs, so. All right. Thank you. All right, thank you very much, Peter.